You write a standard fetch call, hit execute, and the browser console instantly bleeds red, a CORS error. But if you check the backend logs, the server reports an HTTP 200 success. Most developers see that red text and assume the browser acted as a proactive firewall. The assumption is that the browser saw a cross-origin request, recognized it was unauthorized, and blocked it from ever leaving your machine. In reality, while the front-end script threw an error, the server actually received and processed the request perfectly. To understand why, we have to look at the same origin policy. This is the browser's baseline rule that restricts JavaScript from interacting with resources outside of its own domain. Assuming CORS acts as an outbound firewall leaves enterprise systems vulnerable. The intervention isn't a block on transmission, it's a retroactive read block on the response. Before CORS existed, the early web operated in an environment where basic HTML forms acted as open portals, transmitting data instantly across isolated boundaries. Legacy HTML form tags were historically permitted to send post requests to any domain without any security restrictions. Modern browsers are bound by an absolute architectural mandate. They cannot break backward compatibility with the early web. This creates a logic trap. If an old HTML form is allowed to send cross-origin data, modern JavaScript must be allowed to do the exact same thing. The browser handles this through the simple request, a modern fetch call that mimics the behavior of a legacy form submission. Because the browser must support this legacy behavior, it creates a deliberate bypass in modern security boundaries, changing how cross-origin execution operates. We examine the boundary between JavaScript runtime and network stack. The stack inspects outbound fetches for simple request status. First, the method must be get, head, or post. Then, headers must contain only safelisted types. Finally, content type must be form URL-end, multi-part form data, or text.plain. This is where most modern developers trip. Attaching an application/JSON content type instantly disqualifies the payload from being a simple request. If a request fits these legacy criteria, the network stack grants it special execution privileges, bypassing all proactive security checks. Let's map the sequence. JavaScript invokes fetch, passing parameters to the network stack. Because criteria are met, the stack transmits the packet over the internet to the server. The server receives the packet and executes side effects, like updating a database. Only then does the server send its HTTP response back toward the client. The critical takeaway here is that the outbound network transaction is 100% complete before the browser evaluates a single security header. The actual security intervention finally occurs at the exact microsecond the server's response hits the browser's network stack. The network stack catches the response and holds it, waiting before it resolves the pending promise in the JavaScript runtime. Now, the browser performs the explicit CORS check, scanning the response headers for the access control allow origin value. If that header is missing, or if the origin doesn't match the client, the CORS check fails. Because of that failure, the network stack proactively rejects the JavaScript promise, throwing the red error in your console. This means the JavaScript runtime is blocked from reading the response body or seeing the status code. But remember the server action. The front-end memory access is blocked, but the server's database was still updated. For simple requests, CORS is a retroactive read block protecting client memory from malicious data. It is not designed to protect the server. Consider the alternative scenario, a complex data packet hitting an impenetrable security shield that halts its momentum entirely. For modern, non-simple cross-origin calls, the browser uses the Preflight request. When a request includes JSON or custom headers, the browser suspends the primary fetch request within the network stack. It sends a preliminary options ping, asking the server for permission before it ever transmits the actual data payload. If the server rejects the preflight, the browser drops the payload. The server never receives data. Only preflight requests act as the proactive firewall developers imagine. This makes the distinction between simple and preflight requests a critical architectural boundary. We have to translate these mechanics into how we design APIs and front-end architecture. A common failure is relying on CORS to prevent unauthorized state changes, like a malicious cross-origin post request meant to delete a user record. This reliance is dangerous if your backend API is configured to accept application-x-www-form-encoded data alongside JSON. A malicious site can trigger a simple request that executes the deletion on the server. The resulting CORS error in the browser simply hides the fact that the attack succeeded. The rule is that you cannot trust the client environment to protect the server's data integrity. Backend servers must always independently validate authentication and authorization, regardless of the front-end CORS configuration. CORS is designed to protect the client's memory from reading untrusted data. It is never a substitute for true server-side security.